So in this section, we're dealing with U-substitution, which is basically a technique that will allow us to reverse the chain rule, reverse the process of the chain rule when we're finding antiderivatives. So this will give us another method of finding integrals of more complicated functions. And basically, we're going to be able to do this whenever the derivative of one of our factors of our function happens to be or only differ by a constant factor of the other factor of our function. So we'll see how to utilize that. We can write down the theorem as you see here. So if u is g of x and you happen to have some composition and g prime of x is multiplied by it, so that's essentially like our kind of, if you think about the chain rule, you have the multiplication by the derivative of the inner composed function. That's what that g prime of x is acting like. If you can make a variable substitution, then you can go ahead and find the antiderivative. So really, this is kind of about organization when applying this theorem, not so much about remembering anything fancy. Okay, so let's look at some examples where we're trying to evaluate. So let's say evaluate, or maybe evaluate's a bad word since we're not finding a numerical value, but let's say compute maybe each indefinite integral. So for A, let's say we have the integral of 2 times the quantity 2x plus 1 to the third power dx. Again, this is something we could technically already find the antiderivative of without using a substitution, because we could expand the polynomial and then go part by part, but that requires a lot more effort. So substitution here will actually allow us to compute this much more efficiently. So the way that we do that is we let u be whatever looks like our inner function, which in this case is 2x plus 1. So let u be 2x plus 1, and then implicitly differentiate both sides. So the derivative of u we'll say is du, and the derivative of 2x would be 2, and then you multiply by dx since we're doing implicit differentiation here. So then what happens is our integral, we can, there's two ways to do this. Some people actually prefer to solve for dx explicitly. So if you've done this before and you prefer that technique, that is fine. I think that's getting more common. But anyway, so our integral down here becomes the integral of 2, and then we can replace 2x plus 1 with u, so 2u cubed, and then we're going to replace dx with this du over 2. So the 2's will cancel, and we're just finding the antiderivative of u cubed du, which is very easy. This would just be u to the 4th over 4 plus a constant. And then what we want to do is we want to change back to the initial variable. So our initial variable was not u, but the expression that defines the relationship is u is 2x plus 1. So we can say, okay, well, 2x plus 1 to the 4th over 4 plus c. That's our general antiderivative. So that's pretty straightforward. Again, let's do another simple one before moving on. So let's say we're trying to integrate 10e to the 10x. Again, so usually when you're looking for u, you might think about what would you simplify first if doing an order of operations. Imagine you were just doing some arithmetic. In this case, it would be the 10x and the exponent. So that's one way I can realize, okay, that's what I want to let u be. So let's let u be the 10x. So then I know du, the derivative of 10x would be 10, and then I have to multiply by dx. If I want to solve for dx explicitly, I would divide by 10. So du divided by 10 is equal to dx. And then our integral, we could say, okay, this is the integral of 10 times e to the u, and then we want to replace dx by du over 10. And so we just have the integral of e to the u du, which is e to the u plus a constant, and we can replace again u with what it was originally meant to be, which is 10x. Okay, so pretty straightforward. Both of those examples are fairly easy because the constants work out perfectly. Usually that's not going to be the case. So let's go ahead and move on and see some examples where that happens. So let's look at the integral of, say, x to the fourth times the quantity x to the fifth plus 6 raised to the ninth power. Okay, so again, just a polynomial. You can kind of recognize that the inside, or the thing that we want to let represent u, x to the 5 plus 6, if you take the derivative, you're just going to get something times x to the fourth. So that's one way to recognize this is a u-sub problem. Again, let's let u be that x to the fifth, x to the 5 plus 6. So then du is going to be 5x to the fourth dx. So if you're solving for dx now, it's actually going to be kind of like a mix of variables, du over 5x to the fourth. But once you replace dx with this expression, if all the x's don't cancel out, then you've done something wrong. So how does this go now? Well, this becomes the integral. We have our x to the fourth, and then what's inside the parentheses is just replaced by u, so we get x to the fourth times u to the ninth, and then dx we're switching with du over 5x to the fourth. So as you can see, all the expressions of x cancel out. But now the coefficients didn't come out quite so clean, but that's okay. So we end up with 1/5 times the integral of u to the ninth du, and that is an easy antiderivative. We just end up with 1/5 times 1/10 times u to the 10th plus a constant, which we can now write down as 1 over 50, and we can replace u with x to the 5th plus 6 to the 10th plus a constant. So that is our antiderivative there. So the polynomials you can typically recognize the expression that's going to represent u. You're looking for its derivative to just be an exponent 1 degree smaller than what you're letting represent u. Let's look at one with maybe a trig function. So let's suppose we have the integral of cosine cubed x times the sine of x dx. So this one you could actually do either way, but again, it's going to make more sense to let u be cosine cubed because you want to let u represent something in the more complicated part of the function typically. So if we let u be cosine of x, sorry, not dx yet, then we know du will equal the derivative of cosine is minus sine, so we'll get minus sine of x dx. So du divided by the minus sine of x. So sorry about that, my video just crashed and I had to restart. So back to where we were. So solving for dx, du over minus sine of x is dx. So we can transition our integral here. So we end up with the integral of u cubed times the sine of x, and then we can replace du or dx by du over minus sine of x. So the sine of x's cancel, so our expressions with respect to x are gone. We can bring the negative out front, and we get minus u cubed du, and the integral there is just going to be u to the fourth over 4 plus a constant, and as always we can replace u with what it was originally representing, which is cosine, so this is now cosine to the fourth of x over 4 plus a constant, and that is your antiderivative there. Let's go ahead and look at some definite integrals, and the definite integrals are actually nice when they involve a U-substitution, because what you can do is you can actually figure out what the limits correspond to, and then you can go ahead and transition those limits as well, and you will not have to revert back to the original coordinates. So let's look at how that works through a few examples. So example, let's say compute. This one I could actually say evaluate, compute each definite integral. or compute the value of each definite integral. So let's say we have the integral from 0 to 2 of, let's say, 1 over quantity x plus 3 cubed dx. So this is actually a relatively straightforward substitution. We just want to let u equal x plus 3, and then du directly is dx. But let's think about the limits for a minute. So we can actually transition those limits. So we first want to think about our x values. So our two limits, we have x equals 0 and x equals 2. Well, what do those transition to? Well, to find u, you just add 3 to x. So x equals 0 is the same as u equals 3, and x plus 2, or x equals 2 is the same as u equals 5. So we can take this integral now and switch everything over. So this is actually just the integral. Instead of from 0 to 2, we'll say from 3 to 5, and it's going to be 1 over u to the third power du. And we never have to switch back to x this way. So again, since we're still kind of new to this, I'll rewrite this as u to the negative third du. So this becomes, so we add 1 to the power, then divide by that number, so negative 1/2 u to the negative second, and we're going from 3 to 5. So we end up with negative 1/2 times 1 over 25 minus negative 1/2, which turns into a plus 1/2 times 1 over 9. And this evaluates to 8 over 225 if you get a common denominator. So you can check that. So that's it for part A. Let's look at another example. Let's say we're doing, I don't know. So this will be similar to the last one from the indefinite integrals. So let's integrate from 0 to pi over 2 of sine to the fourth times cosine. So again, what is our substitution? Well, we want to let u be sine here because that's one of the factors of the more complicated one, and then the derivative of sine is cosine. So let u equal the sine of x. So then du is cosine of x dx. How about our limits? So x equals pi over 2. That transitions to u is equal to the sine of pi over 2, which is 1. And then x equals 0. We know that the sine of 0 is 0. So our integral over here becomes the integral from 0 to 1 of u to the fourth. And then du is already cosine x dx, so u to the fourth du. So we end up with u to the fifth over 5 from 0 to 1, and that just comes out to exactly 1/5. And that is all. Yeah, so there's one last example in this section that I do want to go over because it involves a trigonometric identity. So, you know, a lot of times people don't focus so much on trig identities, but when it comes to calculus, it really is an important thing because let's just look at this example. So let's suppose we were trying to find, compute, and we could make this a definite or indefinite integral. Let's say compute the integral of sine squared theta d theta. Okay, now there's no obvious substitution to make here, and you know, it seems like this is something that is pretty difficult to get your hands on in terms of integrating, but we do have some identities that we can utilize here. So let's recall that sine squared of x is equal to 1 minus cosine of 2x over 2. So you could ask why. So this is something you should be able to do. So I'll give you a hint to the answer, let's say. So the hint, so let's just say combine sine squared x plus cosine squared x equals 1, the Pythagorean identity, and then the double angle identity for cosine. So, and let's say cosine of 2x is equal to cosine squared x minus sine squared x. So if you combine those two identities and then simplify in the right way, you get the above identity. So our integral right here, integral of sine squared theta d theta, we can actually write as the integral of 1 minus the cosine of 2 theta over 2 d theta. And then this can be broken up into two integrals, right? It can be written as 1/2 minus cosine of 2 theta over 2 d theta. And if we do 1/2 d theta minus the integral, so we can also bring the 1/2 in front here, and then we have cosine 2 theta d theta. Then you can figure out the antiderivative of the cosine of 2 theta via a U-substitution. So I'll leave it for you to do that U-substitution, but you can see basically that your final answer is going to come out to 1/2 theta minus the sine of 2 theta over 4 plus a constant. And again, note that the second integral can be done via U-substitution with u equal to 2 theta. And that's it. So not so difficult there, so I'll leave that for you to fill in the details. But that is one application to finding some indefinite and indefinite integrals where some trig identities are involved. So you also may want to practice. So we could say, so example, so I'll leave this one for you to do, but you should also be able to compute the integral of cosine squared theta d theta. And again, the hint to complete this one is you're going to use the same identities, but we know that the cosine squared theta is going to equal 1 plus cosine 2 theta over 2. And then, you can fill in the details. So anyway, that's it for U-substitution. We will use this technique over and over again throughout the rest of the semester. So it's good to do lots and lots of practice with these. So this is Dr. Lennon signing off.